Hello everybody, I'm Tahereh Ramezani. I am a Ph.D. student at Astrophysics at Masaryk University. I was born in Iran, and when I was in Iran, I taught astrophysics, basic astrophysics to students, children, adults, teenagers, and others. But as I leave my country for my PhD students, PhD studying, I couldn't teach them. But I had some online seminars, but it was limited. And because of that, I decided to continue my teaching, as I like learning and I like to display my knowledge to others. I decided to make some YouTube videos, and but I thought that I speak in Persian, in my own language, mother tongue, but I thought that because many Persian students can understand English and it's an international language, I decided to speak in English. That not only Persian students, but also other students can understand it. So I decided to teach whatever I learn in different courses, in different seminars, and then I want to share my knowledge to you. For the beginning, I start to explain something about star clusters. That my PhD is about Gaia data release 3 related to star clusters, mostly open clusters. Now I can share my screen to show you something related to star clusters. Okay, you see star clusters? Okay, the definition of star clusters. You know that star clusters are a group of stars in a region. They were born from a one cloud, and that we have some star clusters in our Milky Way. The number of star clusters in our Milky Way is 10,000, and 3,000 of them are in Catholic. From these, we have 170 globular clusters and 2,830 are open clusters. Stars in open clusters were born together by mutual gravitational attraction. And I told you that all members of star clusters, each star was born in one giant molecular cloud that we call it by abbreviation is GMC. But in different, not far, but in very small age, in very some few million years. You know that in astrophysics, a million years is not much. It's something that is, we call it low. And all members of individual star cluster have 4 parameters that are important for us. The first one is distance from the sun. The second, age, metallicity, and kinematical characteristic, that it has radial velocity and proper motion and intrinsic speed. I will tell you about them more too. The difference between open cluster and globular cluster. We have 2 kinds of star clusters, open cluster and globular cluster. Open clusters are mostly young and globular clusters are old. What's the difference between them? Open clusters have the age less than 5 gigayears, but globular clusters has the age of the Milky Way. They are very old clusters, and some stars in globular clusters dead already. The distance from the sun for open cluster is more than 45 parsec. Parsec is the unit in astrophysics to measure the distance. Each parsec is 3.26 light year. And for globular cluster, the distance from the sun is 2,000 parsec. More than 2,000 parsec. The mass range of the members in open clusters are complete range depending on the age of the cluster. But for globular cluster, it is less than 20 mass of the sun. It is the symbol of the sun. We measure most of them or all of them to the sun in comparison with sun. The total mass for open clusters are less than 60,000 mass of the sun. But for globular clusters, it is less than 1 million mass of the sun. The absolute diameter for open clusters are less than 25 parsec. But for globular clusters, it is less than 100 parsec. And metallicity for open clusters is -1 to +0.66 compared to the sun. But for globular clusters, it is -2.5 to -0.5 compared to the sun. You see that there are many differences between open clusters and globular clusters. The clusters have some parameters that we measure and they are important. The first, reddening, distance modulus, age, and metallicity. I will tell them too. We call reddening or absorption or extinction. No difference. What is reddening? Consider that we have a star. It is far from us. When I say us, I mean sun or earth. And we can't see the brightness of that star clearly. Why? For two reasons. The first is something that we call it interstellar medium or ISM in abbreviation. That maybe you see in some movies that they show that some interstellar medium, it is dark, but it's not dark really, because there are some brightness of the stars. That interstellar medium absorb that light, that it's limitation that we can't see the brightness of that star because of interstellar medium absorb it already. And the second one is the atmosphere of the Earth. I can say that reddening is something related to redshift. Maybe you know that about the Doppler shift or redshift. We call redshift that something is go too far from us. We call it redshift. If something is come too near us, we call it blue shift. But when something is go far from us, we call it redshift. And reddening is related to redshift. It is something that is far from us, Doppler shift. And in this picture, you see the Hertzsprung-Russell diagram. Maybe you heard about the Hertzsprung-Russell diagram. It's a very famous diagram. In Hertzsprung-Russell diagram, we have temperature or color in x-axis, and we have absolute magnitude in y-axis. What is this? Well, we can read the diagram. For example, O, B, A, F, G, K, M are the type of the stars. For example, we call it O type stars, B type stars, A, F, G, K, M. For example, our sun is in G type star. Why? We call it, the temperature is somehow low. You see, about 6,000. And the magnitude is about 6. Well, how we can read this and understand it? You see that the temperature in Hertzsprung-Russell diagram is from somehow 30,000 to 3,000. So the temperature is here is high. And what about the magnitude? Magnitude is brightness, luminosity, something that we can see, the bright of the star. If magnitude has a minus, it means that it is very bright. The difference between magnitude is for example, mathematics. When something has a plus, for example, plus 16, you see that it's high. But in astrophysics, in magnitude, it is vice versa. When something has a magnitude of minus magnitude, we call it more brighter than others. For example, the brighter of the -8 is 2.5 brighter than -6, and -6 is 2.5 brighter than -4, and so on. So the magnitude of plus 16 is very, very low, that we cannot see that star with our naked eyes. For example, the magnitude of -6, we can see it with our naked eyes, very perfect. But the magnitude of also 8 or 10 or even 6 in megacities, we cannot see that stars. So now we understand the x-axis and y-axis, and also the name of this. What is this? We call it main sequence. That stars in main sequence, they pass their life. The stars are like us, our people, human. Why? Because, for example, sometimes they was born in a giant molecular cloud, and then with the first diffusion, we see that star. We call it one star was born when we see the first brightness of that star. Then they go to main sequence. First, they are young. They are somehow, we can call it child, and then teenage, young, and then middle age, and then old, and then they will die. So the stars in here are so young. Why? Because the temperature is very high. You see, 20,000. It's very high temperature. And also the magnitude is -2. So it is very young and it is very bright. That the blue are bright, white and yellow is somehow, I can say middle, and red is no. They are somehow old. And then, for example, our sun, it is somehow in the middle of the main sequence. The temperature is somehow around 6,000, and the magnitude is around 6. So it's a middle age star. It's a typical age. It's not a very special star. And then we see Proxima Centauri. It is 3,000 temperature. It has about 14 magnitude. So it's a very old with low temperature and low magnitude star. So then we see something else. We have some other regions. What are they? We call this region for giants and supergiant stars. Why? Because they are, you see that the radius of these stars are much more than these stars. So they are in the somehow in the end of our day life, and they are very large, and we call it supergiant stars. For example, Betelgeuse in Orion constellation. It has a 3,000 temperature and about 4 to 8 minus 4 to 8 magnitude. It's a question that in our mind, we say that something that has a low temperature, we couldn't see that. In our real life, when something has a low temperature, we can't see it. But how it has a high magnitude? Why? Because of their surface. The luminosity or magnitude or brightness is depend on the surface. And because their surface is very large, we can see them very perfectly. They have a -4 to -6 magnitude. Also for giants. And we have the other region. We call it some stars that we call them white dwarfs. They are really near to the end of the life of the stars. They have very low temperature. You see low temperature, and the brightness or magnitude is very, very low, 10 to about 14 or 16 magnitude. Plus 10 to -14, 16 magnitude is very low. So we somehow cannot see them. Of course, not by naked eyes. And also, after that, we have something like brown dwarfs that we cannot see anything. So we can say that these are dead. And the formation and evolution of stars. As I told you, stars with all masses form in a star clusters. In our star clusters, we have different stars with different masses. But mostly, stars were born with low mass, and we have very few stars with high mass. And high mass stars, they use their mass very soon, sooner than stars with low mass. And they use diffusion, they rotate very fast, and they use their mass very much sooner than low mass stars. And you see that here there is a proportion between luminosity, L, and mass of the stars. And the last thing that I can say is HR diagram for various open clusters. You see it is somehow like main sequence, and there are different open clusters. Open clusters in here, as I told you, they are young. They are younger than others. For example, H and He per se is younger than M41. And for example, M67 is a very old open cluster. And you see something here, turn off. We call it turn off point. What is it? When, as I told you, in our star clusters, we have different stars with different ages. that they were born in different ages in a few million years, but the mean or the average age is somehow near to each other because they were born in the same giant molecular cloud. And then in some time, after a while, the stars of that star cluster leave the main sequence. When they leave the main sequence, we call it turn off point. It's the point that they turn off the main sequence and they go to other places, giants, supergiants, and others. So it's related to our Hertzsprung-Russell diagram, color and magnitude, absolute visual magnitude. So in this time, I told you about the main parameters and something related to star clusters, mostly open clusters. I will tell you about more in the next session. Have a good time, and I hope that you use and it was useful for you. If you have any questions or comments, do not hesitate. Please ask me. If I can, I will answer you. If not, I will ask from my supervisor, Ernst Ponsen, or others, and then I answer you. Have a good day. Bye. See you.